probably obsessively see how many people are actually watching this. Oh my God, look at the comments.
So everybody go in and put comments in there when it's online, how fabulous it is, and how wonderful it is, and how we're so grateful you came.
Oh, you know that people, like random people, are going to put comments like this.
This is true.
You know, this, and then words you can't say in a colloquium and things like that. I'm always amazed at the comments. It's just...
I know that so far a few people have come in to watch the YouTube videos, and someone from Alaska was on it. We don't know who. All we know is where they're from. And so we've been a great debate trying to figure out why someone from Alaska would watch our colloquium. But so we're getting worldwide, well, nationwide representation. I'd like to introduce Shobhana Murali. She received her PhD from Georgia Institute of Technology in the fall of 2001. After a year of postdoc work at Lehigh University, she stepped away from academics to spend more time with her young kids. She rejoined the workforce a couple years ago and is currently teaching game theory at UC Berkeley. She's primarily interested in functional analytic approaches to Markov chains, including discrete curvature, isoparametric inequalities, and statistical physics. So it's my great pleasure to introduce Shobhana Murali.
Thank you. Good afternoon, everyone. It's anticlimactic to say good afternoon after I've been standing here chatting with you for 10 minutes. But thank you, Cora, for giving me the chance to talk at your department colloquium. I'm going to talk about notions of curvature for Markov chains. It's going to be a discrete notion of curvature. This is actually something I worked on my thesis, which seems like eons ago now. And I stepped away from math and just totally immersed myself in my children. And now I've come back trying to teach, primarily because my mother said I have a PhD and I better get off my bottom and go do something. So I did. Anyway, it's great to, I taught at St. Mary's for a couple of years now. I'm teaching at Cal. Be unemployed next semester, so if you're looking for someone. And then employed again in the summer. But anyway, so that's the life of someone coming back. The point of this lecture is, it was very encouraging and gratifying for me, when I started reading math again and reading papers. It was kind of exciting to see that after all these years, people were interested in curvature again as a notion. There's been a spate of papers published on people trying to look for an appropriate definition of curvature in a discrete sense. I mean, we all have an idea. Pretty much everyone says, oh, curvature, yeah, I can kind of describe to you curvature. You have a sphere, it's positively curved. You have hyperbolic space. You have negative curvature, and then a plane is flat. So we kind of know this, but what do we do in a discrete sense? Curvature is very intimately linked with the calculus, being able to take derivatives and so on. So anyway, so before we actually get to the notion of curvature, I'd like to describe why people care so much. What are some of the problems that motivate this search for an appropriate definition, and give you some of the problems that people have worked on. And the ideas have been drawn from many different parts of mathematics, from geometry, of course, probability, functional analysis, PDEs, and I can safely say I'm expert in none. So, but I know a little bit of probability, perhaps, and I try to go through the rest. But anyway, so what I did in my thesis was apply functional analytic techniques to various inequalities on Markov chains. And now what I'm going to do is go back to the problems that people have looked at and try to give you a flavor of the journey that's still going on in searching for this. And I think it's quite exciting and interesting and so on. And I hope you do too. And something might spark your interest in this talk. So let's see. Do I go this way? Or this? Neither. Okay. All right. How do I page down? All right. Okay, I did the arrows because that's what I do in my math. But all right. The first problem is about optimal transfer, and we'll describe what it is in a setting. But the idea is that you want to transport some mass from one place to another, and you want to do it with as cheaply as possible. And then concentration of measure, which is a phenomena in which a function will basically stay close to its average value under certain conditions. And convergence of Markov chains. Now, as one of the audience members said, well, I don't know what a Markov chain is. Not to worry, we have a nice basic example, and from examples we will try to figure out what they are. And it should be enough. All right. So the problem of optimal transport goes back to the 18th century. It's about Gaspard Monge, who was born in 1746. He was born in the French ancient regime. And he went to military school. He was absolutely brilliant. And so that's why he was allowed to go to military school in spite of his rather modest background. And he was a geometer, and he was absolutely excellent. And in fact, he became a professor at 22. He was a very, I've read about him that he was a very ardent warrior scientist and became consequently a very close friend of Napoleon. And while studying, and he used to work for the military, investigate things for the military, and he wasn't really allowed to talk about them that much. But in 1781, he published one of his rather famous works, Memoires sur la théorie du déblai et remblai. That's an Indian faking a French accent right there. But I have an unkind French friend who said it's okay to do. So anyway, the point is that this probably occupies military all over the world. You dig something, you dig up mud or dirt from the ground, and that's the déblai part, just some earth that you take out from the ground. And then you want to transport it to a different site and build something out of it, a wall, fortification, something. And you know exactly how this mud is in the place where you're digging it out of. You know exactly what it is that you want to build. So you know what the shape of the thing that you want to build is. And the only problem here is you want to not spend too much doing it. You don't want to expend too much work. You don't want to spend too much money. And one would think that the money is related to the distance that this material has to go, to travel. So Cédric Villani, who's a French mathematician, and he's he's brilliant. I was fortunate enough to have a course from him. Anyway, he gives a nice little example in his book, Optimal Transport, Old and New. And this is a more discrete example. So this is, as you see, continuous. You have the mass, and you take it, the earth from there, the mud, and you take it to this building. And here you can imagine that your space is Paris, the city of Paris. Paris has a lot of bakeries and a lot of cafes. So the bakeries bake loaves, the cafe people eat the loaves. So you have, and the distance is the natural distance metric. You want to go from one place to another. How far is it? You have an idea of that, of course. So now you have the loaves, and the B's represent the bakeries. And you know exactly how many loaves are produced. And you know where they're produced. So you know the production density. And you know the consumption density. You know who's in the cafe. Let's suppose you know who's in the cafe. You know how much they want. Now the only problem is that you have to take the loaves from the bakery and you want to take them to the cafes with minimum cost. So it's the same problem. So the problem actually comes down to being one of a coupling. So you have a joint distribution. It's a coupling of these two densities, these two measures that you have, the production and the consumption, and in some optimal way. So looking for an optimal coupling. So if we set it up, we can go to a graph now. So a graph is it's just a bunch of vertices which will represent whatever states you have. And you have edges connecting them, say like that. And so V represents the set of vertices, E the set of edges. You have a probability measure defined on your vertices. So you have, if you don't, just think of you have a mass of 1 kilo and you want to split it up and distribute it over all the vertices. There's your probability measure. And you have a distance D, which is very, I mean, it's quite natural what you would think of. How far is this from this? Well, as long as it takes to get there, which is one edge. How far is this vertex from this vertex? And it's 2. The shortest path to that vertex. You have probability measures on your vertex set. And so again, probability measures are some distribution of mass among the vertices. And the problem is one, like with the bakeries, you want to reconfigure the mass distributed according to nu 1 to a mass distributed according to nu 2. So that's what mass transport is. So how are we going to do it? We're going to do it with a coupling. So you're going to take a joint distribution. So you have a probability measure in V cross V. So now you have ordered pairs of the vertices. So that the marginals give you the measures that you're interested in. So you have an optimization problem. You want to minimize the cost. So you have the probability. So you have this coupling. Then the cost is going to be proportional to the distance. So you just say the cost function is the distance between x and y, subject to the marginals being the appropriate measures that you're interested in, and of course it has to be non-negative since it's a measure. So then many years passed, and that was what Monge worked on. And then in the USSR, in the early part of the 20th, also the mid of the 20th century, Kantorovich worked on it, and he also, in fact, he had some parallels with Monge, that he was also very young in his early 20s, became a professor, completely brilliant. He also worked on military problems, wasn't allowed to discuss them, and he, worked on stuff for the war, and which war? Well, maybe the Cold War, maybe, I'm not sure. He was born in 1912. But he actually discovered a lot of the precepts of linear programming. The Soviet Union just didn't want to talk about it. But in 1975, he got the Nobel Prize in Economics for his contribution to the theory of optimum allocation of resources. What he did also was he constructed the dual to Monge's problem. So remember, Monge's problem was an optimization problem set up where we look for an optimal value amongst all the couplings. He set it up as we maximize this quantity. So you have your two measures, nu1 and nu2. Your measures nu1 and nu2, and you optimize over all functions g, appropriate functions. I put a d over there because otherwise, if you don't have the d, you might tend to forget that the d is very crucial, the distance, the cost. So you want for all x, y in the set that you're interested in, the distance between gx and gy should be smaller than dxy. When a function actually looks like this, it satisfies this property. It's called Lipschitz. So you do it over all Lipschitz functions. And he proposed that you take this optimal value. I call it the joint optimal value because since it's a dual to Monge problem, the optimal value for this will also be the optimal value for the Monge problem. And you use it to define the distance between two measures. That is the optimal transport cost of moving the mass from here to there will be the distance. This distance is called it's got many names. You might have heard of Hutchinson distance, Wasserstein distance between two measures. Krove stands for Kantorovich, Rubinstein, Ornstein, Wasserstein, and it has various names. I think people who work on fractals and images might call it Hutchinson distance, if you've seen that. All right. The next problem that people looked at was concentration of measure. And we first just look at quickly concentration of the sphere. This was first looked at by Paul Levy in the in the 20s, 1920s. And it was reintroduced and looked at more deeply by a mathematician named Millman in the 70s. He was looking at Banach spaces, and he reintroduced the concentration of measure, which has actually many applications. People are very interested in it, and how you might get this phenomenon. How would a measure have concentration? So on the sphere, what it's saying is that the surface area of a high-dimensional planet is concentrated near its equator. So if you're on the Earth, and the earth is completely covered with grass, and it's your unfortunate task to mow it, right? And you have a giant lawnmower, suppose, and you're a giant and all that works. So here's the planet, here's the equator, and say here's a strip, maybe the strip's height is h, this angle, spherical angle is alpha, your radius is rho, and it's not very hard to compute the width of the strip here, and your lawnmower mows along this strip. So what would you expect? Well, you would expect if alpha is small and you take a strip around the equator like that for a small alpha, you're not going to finish very much of the grass that you're supposed to cover, right? So you have to mow all the lawn, and you're going to say, okay, I'm going around the equator, I have a strip, and if alpha is say 10 degrees, you can work out how much you will cover. It's actually, I think, sine alpha by 2. And it works out to be about 8.7%. So this isn't a surprising result. You might say that, all right, that's believable. I'm going around with my lawnmower and I go through this, it covers this much, and I know that I haven't even got through a tenth of the grass that I have to do. So what I've shaded in here, sorry, I keep pointing at the computer, and I should point here. What I've shaded in there in the first one is approximately 90% of the surface area is the gray. But then you go to a high-dimensional planet, and your intuition will fail you. The incredible thing is that most of the surface area, when you go to a very high-dimensional planet, is in a thin band around the equator, which is very counterintuitive, but good for you and your lawnmower. So, because you'll just go and, you're done in one round. You've got 90% of the area very easily. And so, this phenomenon that when you go to high dimensions, you go to a sphere in high dimensions, and the surface area gets concentrated around the equator. This is called the concentration of measure phenomenon. In fact, you can have there's a visual description suggested by Gromov, who was a geometer. And he said, okay, you think of the measure as luminosity. And you say that your eye cannot distinguish a set if it's not got enough size, it's not got enough weight, not enough mass, all right? So if the measure is small, so parts of Sn that have measure less than kappa, where kappa is small, but it's positive, but it's very small, you can't tell, it just looks dark to you. And the more mass a set has, the brighter it shines. And there's some light source and it's shining bright. So if you think about it, when you're in S2, that is on our planet, and it's kind of diffused, you have everywhere it looks kind of light and you can see all the surface area. Then when you go to some strange planet, which we can't really imagine given our limitations, but you go to some very high dimensional planet, and it will shine a very bright light, band of light around the equator, and everything else will be in darkness.
Question?
Yeah.
Well, what do you mean by equator? Any great circle?
Any equator will do, actually, by symmetry.
But so every great circle has this 90%?
Right. It's very strange to think about, bend your head around it. Yeah, because it's completely symmetric. So any great circle, it's concentrated around that. The area is concentrated around that. Yeah. I mean, for the purpose of luminosity, you have to say, okay, there's a light source and then one particular, but actually any circle, yeah. All right. So that is a sphere. I just did this because it's kind of nice to see. We can look at the discrete analog of the sphere, which is the discrete cube. So you can take, coin flips. That's your random variable. You flip a coin. If it's heads, you take 0. If it's tails, you write down 1. Probability of half of seeing all of them. Now take it n times. So IID, independent and identically distributed random variables. Then you look at their sum. And you know that if you see this, if you look at this n tuple, this is on the discrete cube, which is 0, 1 to the n. All right, the standard discrete cube. So you do this, and And a concentration of measure phenomenon on this, we have something that will play the role of an equator where you just take a sort of diagonal. If you have n is equal to 2, so this is 0, 0, 1, 0, 1, 1, 0, 1, and n is equal to 2, so you have something like that. And on a higher dimensional cube, you'll have some sort of hyperplane. And basically, if this set plays a role of an equator, I mean, you take the floor if n is odd of n over 2, and this, most of the vertices get concentrated around in a strip around the equator, and the width of the strip stays constant. So as n gets very large, you're looking at a very small fraction of the width really gets very small compared to the width of a strip containing the whole cube. So the strip gets thinner and thinner, and it's I was going to derive this, but maybe I won't. It's a consequence of what's called the Chernoff bound. If you've ever seen that, it comes from there. That's really a discrete analog of concentration on the sphere. And so the Chernoff bound tells us that you have the probability that it lies in this strip over there with this width for some lambda, positive lambda. Then outside this band, x minus n over 2, so you go is greater than lambda over root 10, takes you outside a strip, and that probability becomes small as n gets bigger, very small relative. So again, finally, what is concentration of measure? It's just saying that nice functions, nice will depend on what you want, almost always stay very close to their average value. And in practice, what we do is we look at a subset of the vertices, some A, and you look at the enlargement. So you take A and you take some h, positive h, and then you just take everything at a distance h. All the x at a distance where the distance is less than h. So this is basically what it looks like. Just take a little band around it and the set itself. And then you have a concentration function. So what does the concentration function do? It says we take all large sets of measure at least a half, so their size is at least a half, and you take AH, which is a little enlargement, and then you look at what's outside. And that's your alpha of h. Now, if you can find constants that this alpha of h is bounded by this exponential bound, so you can find constants k and c so that this happens, you say that the measure has exponential concentration. That means things are getting concentrated around its, usually around its average, its median that you're going to consider. Or you can have something even better, which is called Gaussian concentration, normal, because you have an h squared. So now, someone might say, hey, what's the big deal on that? You're in a finite graph. I can always find k and c so that this is true. So it'll work for some k and some c. And yeah, sure. So it's not really interesting on a finite graph, but when you take products of finite graph, which is what people do very often, then you're going somewhere with this. All right. The last motivational thing is Markov chain Monte Carlo, which I think many of you might have seen some of. So these are a computational method for studying large sets. In particular, it gives us an efficient way to approximate integrals. So if you know what your distribution is that you want to approximate, but you just can't write it down explicitly, or it's just too difficult to compute an integral, then you just use the Markov chain Monte Carlo. You construct an appropriate Markov chain, which you hope you run it long enough, it will converge. You trust it will converge to your target distribution. Once it converges to your distribution, you sample from your distribution, and then you take your empirical mean or whatever you're looking for. You can compute your integrals with your sample. So I just put down x is minus 1, 1 to the g, and your measure is a Gibbs measure. And we'll come back to this. This is to do with something called the Ising model. It says basically take a graph, and I'm going to do a very big graph, small one. And minus 1, 1, and this is my g. All right? I just take every vertex and I label it with a 1 or a minus 1. Say like this. And how many possible labelings do I get? Well, I can label each one of these with a 1 or minus 1, so I have how many? How many possible? 2 to 3, exactly. So you can see that if G is relatively large, you're soon going to get a very big space of configuration. And the Gibbs measures a certain measure on that space, which comes out of physics, and we'll actually see it in more detail in a bit if I talk faster. All right. So let the Markov chain evolve until it reaches this target distribution. And don't worry, I mean, these words, if you haven't ever heard these words, they'll get clearer in a minute. And the burning question on anyone who does simulations, well, how long should I do this for? Because, you know, you're running these simulations on some computer, you have a ticket for a certain amount of time, and then you have to stop. So then you want to know how long will it take, and is there any way to do it faster? Can you give me an estimate? So people are constantly looking for ways to improve estimates on the time to converging to the target distribution, because it saves days on some supercomputer and makes your boss happy. So that's worth it. All right, so now basics. These are the promised basics for Markov chains. So this is a standard example with the weather. The weather has only 2 states, sunny or cloudy. So we're in the Bay Area, say, right? Foggy or sunny, mostly foggy, I suppose. So with tomorrow's weather, twice as likely. So if you're sunny today, you have a 2/3 chance of it being sunny tomorrow, 1/3 chance of it being cloudy tomorrow. And you can construct a transition matrix. So you can tell that my mental age is like 6, right? Or somewhere between 3 and 6 with this. So this was my favorite, like, oh, let me draw sun and cloud. And so that explains the probabilities. You can go from sunny to cloud, sunny to sunny. So today being sunny, tomorrow is sunny with the probability 2/3. Today being cloudy, tomorrow is sunny with the probability 1/3. Today being sunny, tomorrow is cloudy with the probability 1/3. And today being cloudy, tomorrow is cloudy with the probability 1/3, now 2/3. And then this matrix that we construct, which describes how you go from the state of cloudy to the state of sunny, is called a transition matrix, because it describes your transitions. This matrix is stochastic. That all that means is if I add up the rows, I get 1. It so happens that this one, I add up the columns, it gets 1, but that's not necessary. What you want to see, I want to add up the rows. So each row is a probability, right? So you start with sunny today, then the probability will be cloudy day after tomorrow is, so it's probability that will be sunny tomorrow and cloudy the day after that, or cloudy tomorrow and cloudy the day after that. So that's your probability of being cloudy. And so we got that by multiplying the matrix. If you keep on multiplying the matrix with itself, you get probability of being sunny or cloudy. It gives you both. N days from today. And with this matrix, I mean, if you've seen this matrix, you know what happens. You multiply it a few times and then it just settles down and it tells you, no, it's all right. It doesn't matter what it is today, life is okay tomorrow or in 10 days. So it settles down to telling you that no matter what the weather is today, the chances of sun or cloud in about 10 days is a half. Flip a coin, doesn't matter. So that's what it settles down to. I mean, if you take that matrix and you multiply it out, you'll see after 5 times of multiplying, it's close to a half in every entry. So that probability vector that you get at the end, 1/2 is called the equilibrium measure, and we usually denote this by pi. So let's see. We can also look at the continuous time Markov chain generated by L, and so, of course, L is called its generator. L for us, we'll just use K minus I, where I is the appropriate identity matrix that you're looking at. Now for a continuous time Markov chain, again the transition from state to state, the probabilities are given by the transition matrix, the kind of transition matrix we saw. We can also look at what's called a transition semigroup, but this is functional. And what you do is you just take this L and you take this matrix exponentially, get a matrix, and we call that PT. All right? It doesn't matter for this talk if you know what semigroup means or not. But what does matter is we get a probability measure. PTX dot gives us. So you plug in something, the value of that gives you the chance of going, if you're at X, then T, you get the chance of going to Y. Now the thing is, what's the difference here? Well, in the earlier one, we moved every time instant, jumping according to the probabilities we saw. What happens here is we just sit on a state. We just sit, we don't move, and we have a clock that the alarm to the clock goes off at exponential times. That means if you have an exponential random variable with parameter 1, it rings after a time distributed according to that. Tongue, it goes off, you jump according to your transitions. Then you just sit. And then the alarm goes off, you jump again. And this is, if you've never seen this before, it's not important to you now. What is important, I just put that there, that we're just going to assume conditions to say it is going to converge. All right? Now here's an example, a slightly more complicated example than rain and cloud. Oops, we start with the transition matrix, we let it evolve. And so we start with some distribution, and then this distribution starts diffusing along the Markov chain, and again we're interested in how fast does it go. So this is where I have this thing which is not coming up. Okay, this is the Mathematica that should come up, so I'm pressing.
The flag is the control?
What?
The flag is the Apple key?
Yeah, I'm pressing the flag and tab, but it's not going to, so I'm going to have to escape and go there. Alright, here we are. So let's evaluate this notebook and update. So what's happening is that we have something called Glauber dynamics going along here. And we'll see what, in a second we'll go off and see what exactly the probabilities are happening here. But now you have, instead of -1 and 1, you have black and white. So you have your little pixels colored black and white. And this is showing you every update. Now, if I wanted to go faster, I'm going to have it show every, I don't know, 35 updates. So you see it moving a bit faster. This slider over here, if I move it up to 1, 1, it's going to make them try to align with each other. So now black and white are kind of fighting, and one of them will win. And if you let it run far enough, you'll see that only one color will win. So this is called the easing model, if you've ever wondered about it. I got this off of someone's blog, so I don't know very much about the implementation. A little bit changed a little bit here, and then I can tell you. The blog is called Spline, but shame on me, I forgot the person's name. So now we go back here, and let's do slideshow again. Oh no, we went all the way back. Oh, this is awful. So life is flashing before its eyes, right? So here we are. So this measures as you can see, it's going to turn out to be quite a complicated probability measure over here. So you have your -1, 1 to the g. Remember, it could be the grid, and on every vertex of the grid you throw 1 or a -1. These are called spins in the easing model. So it originally started out as a representation of a magnet with up spins and down spins, positive spins and negative spins. You have an energy functional So S is a configuration. It's some arrangement of +1s and -1. And so if Sx and Sy are the same, this will be 1. If they're different, the product is -1. So for every x, that sign means neighbor of y. So for all the neighbors, you look at this product, and H is some external field, which an external field basically tries to make everyone go a certain way. And that's what you have. Now, you have some constant beta greater than 0, a Boltzmann constant. The Gibbs measure is defined as this exponential. You look at this function, you stick it here with this beta. And Z is just a normalizing constant, makes it a probability measure. So, the measure of the whole space, the whole configuration space is 1. So you can see it's sort of a complicated measure over there. And so what you usually do is you simulate it and you try to figure out stuff based on that. The second negative down here in this setting means that the states where Sx and Sy are the same, they tend to align together. So they're the same, and those get more weight with this measure. All right. Now we come to constants. So if you've heard of the spectral gap, traditionally the spectral gap is the constant that says how fast your Markov chain is going to go. So you remember, you have your Markov chain, you're running it along, that means you just basically, you have some means by which you let it run. You let it evolve, it goes, something is flipping coins for it, it's deciding where to go, and it's going on its way. It's jumping from state to state to state, and you're recording which states it's visiting, and it's just jumping around. And then you want to say, well, how long does it take to settle down into its equilibrium, where it's not jumping that much anymore. And it converges to its stationary distribution. This is called mixing time. And it's been measured in what's called the total variation distance, where you just look at how much the measures actually differ from each other. And you look at the maximum of this. So I'm going to skip this mixing time and go to the Perron-Frobenius theorem. Has anyone here seen that before? Okay, so the Perron-Frobenius theorem is kind of hoping others would have too, but it basically tells us that if you have an irreducible finite, irreducible for us is going to, it means that you can get from any vertex to any other vertex. There is a path to go to any other vertex. There's not some vertices just lying by themselves, isolated. No, everyone's in one clique, if you want to call it that. So it's a connected graph, if you've looked at graphs. So you have an irreducible finite state Markov chain, and it will converge to equilibrium exponentially fast. What it doesn't tell us is, well, how do we get a handle on that? So we look at the smallest non-zero eigenvalue of this matrix. Remember, we said L is k minus I, so you're looking at minus L. And this eigenvalue controls the rate of exponential decay. All right. I am not going to tell you how. You'll have to take it on faith and thank your stars that I'm going to skip that. We finally, after all this, come to curvature. So people are very interested in what the spectral gap is, estimates on the spectral gap. Because you say, oh, eigenvalue, that's pretty easy to compute, right? Sure, and small matrices, no problem. When your matrix is very large and sparse, then it's not that easy. So then you're looking for things which you can compute. So on a manifold, like a sphere, you want to think of a sphere as your sort of representative manifold, is the amount of distortion you have as opposed to a standard ball. So you take your basic ball of unit ball and Riemannian manifold, and you see how much it differs. It also controls, if you're on your manifold. So let me just do it here in words, it's easier. You take a point x and you take a small tangent vector, unit tangent vector here, and you take the tip of that vector and you call it y. So it's in your tangent space. So remember this, so you want to think of your sphere, you've taken a point and you have a tangent plane here, taken a small vector, then you go to another point y. take a geodesic, so you have a distance between x and y, you make and these points are very close together. Now you take a small sphere around it by taking another tangent vector, and the tip of that is on this sphere. And you look at the tip of this, and you see, are these closer together than this? In Euclidean space, they're the same distance. You're going to get a rectangle. If you go to any kind of curved space, this distance is going to be different. If your space is positively curved, they're going to go together. If it's negatively curved, they're going to go apart. So think of a sphere. Your geodesics, what I call geodesics, are your lines of longitude, the meridians. And if you're on the equator, what happens is you go along the meridian, do you get closer or further apart? You get closer together. So that's what happens on positive curvature. You move closer together. Negative curvature, you move apart. And so this is something that we were looking to replicate. And how would you think about this? So this, why do we care? Why do we care about the curvature? And it comes back to our problems. What happens is the Ricci curvature on a manifold is intimately connected with the solutions. It gives lower bounds in spectral gap. It gives you what are called isoperimetric inequalities. It gives you concentration of measure. It gives you solutions to mass transport problems. So positive curvature on a manifold gives you all kinds of things. Negative, so positively curved in this case implies that this Ricci curvature, which is you take an average over the whole sphere, is somehow saying, all right, as long as I'm positively curved, I kind of look like the sphere. So you can do all kinds of nice things and get all kinds of nice results. You have exponential convergence to the stationary measure if you run a Markov chain, and so on. So these are the things that people used on manifolds. Now in a discrete setting, if you had an appropriate notion of curvature, you could use all these techniques that people use, all the geometry people have in a continuous setting, on a manifold, on a sphere, even on a saddle. Surface. When I say manifold, think of just a surface. And you say, all right, so if I have Ricci curvature, I can look at, stuff on graphs, on Markov chains, because in the end, when you're in theoretical computer science and physics and probability, you're really interested in Markov chains. What happens is it jumps around. And so you want to replicate these techniques and maybe find out more about concentration and convergence to equilibrium. And because we don't have it, we don't have a good notion of a gradient. I mean, we have a notion of a gradient, but it's not as nice. I mean, in calculus, you can easily differentiate. So we don't have something like that, so we can't use these techniques. This is actually what I did in my thesis. I used a lot of functional analytic techniques to try to develop this notion of curvature, And so we have a few candidates, and the Ricci curvature is also linked to the metric that you have. So you have a metric space and use it. So what would we use? It's not quite clear yet. So one candidate is called gamma curvature, this was introduced by Bakri and Ledoux in a paper from 1992. They had what they call a curvature dimension inequalities, and they applied it to Markov semigroup. So they were in a continuous setting. They had no problem. They differentiated with impunity. They took expectations. They took second derivatives. It was wonderful, and they got really nice results. And so I actually read that paper, and it got very cool. And I was very excited about saying, okay, maybe since it's on Markov processes, I can reproduce this and get some results for discrete chains. And it didn't work completely. It was enough to get me out of tech, but it wasn't enough to get really good bounds. So what happened was I was interested in finding an upper bound on the spectral gap. So we all have a lower bound on the spectral gap in terms of something called conductance. Now I'm going to say something, you haven't heard the words, whatever. Conductance for a graph is something that measures how fast things go out from a set. All right? So you can imagine people will be very interested in this. You have information. How quickly does the information diffuse over the graph? This is crucial to know. And so so what happens is a spectral gap is bounded below by the conductance. This was done by someone called Cheeger, and it's a very, very important result. And the corresponding upper bound, so you have bounds on both sides. So you have the spectral gap sandwiched between the conductance on both sides. So you know it's very linked. Was given by Boozer on a manifold. And I was trying to reproduce Boozer's inequality, which I couldn't. I just couldn't do it. And I didn't have there were no tools in the discrete setting. But it would have led to some families of graphs. It would have been very useful to know. Anyway, there is something called the iterated gradient. And what you're going to do, this is the one you should pay attention to. So this gamma 2 is sort of playing the role of a second derivative. That's why it's called the iterated gradient. This is like a first gradient. It looks at the function value at a point, and the difference is when it moves to the neighbors, you take the average, and that gives you gamma. What gamma 2 does is says, all right, I look at the points at a distance 2 from the point I'm interested in, and I look at the differences of the function. So iterate the gradient. I look at differences twice. Look at it over here and then over here. And that gives me this gamma 2. And if this inequality is satisfied for all non-constant functions, for some constant r, then we call this r a lower bound on the curvature. This is what we're going to call curvature. So this is called gamma curvature. So this gamma and gamma 2 have k in them in the definition of, you see it's right here, L is k minus I. So that's what is helping you look at the differences. And you take this ratio, and you see this is always non-negative, but this can be negative or positive, and that tells you if your curvature is positive, negative, or 0. And if your function does not change on parts of length 2, you get 0. So that means the second derivative is 0. So again, you might think, all right, the complete graph is kind of like a ball. I should have positive curvature. I should have positive curvature on a discrete cube because it's like a sphere. And maybe on a path doesn't have any curvature, it doesn't curve, so I shouldn't have any curvature there. In fact, okay, I'm going to skip this. That's what happens. So let's look at examples on a 2-point chain. So 1 point, 2 points, no loops. And half-half. So k is not 0, 0, 1, 0, 1. You go with probability 1 from here to here and probability 1 from here to here. And so this is just to show you roughly what kind of computations are, and you get your curvatures too. If you allow loops, and then you get this minimum here. Now this 2-point chain is not very important. What is important is this tensorization. That means when you take products, you still can, if you know the curvature on a graph, you take n tuples. Just take this graph and multiply, take the product, and you'll get a curvature for this product graph, which makes your life much easier. If you're interested in the discrete cube, all you need to do is look at the 2 points. And then the complete graph, do you know what the complete graph is? You just attach to everything else. Every edge is connected to every other edge. The 0 here means there are no loops. You cannot stay at an edge. You have to move. I left out the computations because they got ugly. So since I've shown you so many, you might wonder, oh, what was ugly? But they were ugly. So this, at every point you did the same thing, n plus 2 over 2 times n plus 1, and then you take what you call the curvature is the minimum of all this. And in fact, it was so this is all stuff that I had done when I was writing my thesis, and I couldn't publish it, unfortunately, because someone else had the same idea. And so if you look at it, there's a gentleman, Schmackenschlager, and he, in fact, of course, you'll read this paper by Bakri Ledoux. It's a wonderful paper, and he did it, and he, of course, is famous and he's a geometry guru, and he published it and it was done. So there you go, that's how you get scooped. But so now it's called Schmackenschlager curvature. It's a little bit faster and might have been a bit different. So what is interesting for paths is that it turned out to be 0 for n greater than or equal to 5. Again, your intuition is just that you're looking at gradients. So what happened was, this was the first approach to a notion of curvature, well, on Markov chains. There is, of course, notions of curvature for graphs, but I don't look at those. Where you embed a graph on a manifold, you look at what is called a triangulation, and you look at curvature for that. But I don't look at that. I just look at Markov chains. Actually, this is an interesting one. Have you seen this graph? It's called the Peterson graph. It's kind of twisted. Every vertex has degree 3. That means it's connected to three other vertices. But it's not two pentagons, one inside the other. It's one pentagon outside and then twisted star. And this one turns out to have, you go with uniform probabilities to all your neighbors. And this one turns out to have negative curvature, which is kind of strange, right? It's some weird thing. Anyway, the Peterson graph again by itself, all right, no one cares, but you take products of the Peterson graph and then people are interested in this. So other definitions of curvature, what is called the Wasserstein-Ricci curvature, which goes back to our idea of the Wasserstein distance. And this is perhaps better because curvature and optimal, the whole reason I talked so much about optimal transport was positively curved Ricci curvature is very crucial in the solution of that problem. And that's all I can say because it's really very, very difficult. There's a lot of PDEs involved and it's just really high-level stuff there. But it has to do with what they call an entropy functional and positive, non-negative curvature on a manifold. So based on that, about 4 years ago, Stern and Renesi came up with a Wasserstein-Ricci curvature on a manifold, some lower bound on Ricci curvature. So again, you're looking for different approaches to give you the curvature of a manifold. And so since you don't have any real geometry on the graph as such, what you can do is take those approaches and replicate them and hope to get a notion of curvature for your Markov chain. And eventually you want to link it. You want to understand something with the structure of the graph maybe. So that was done by Stern and Renesi. They used it for measuring convergence. Now what I personally found very exciting is a new paper by this guy named Olivier in France. And it's also based on Wasserstein distance. And he actually takes that little, remember that little diagram where you have the Ricci curvature. This is X, this is Y. And you look at the geodesics through here and you see if these are closer or further, closer together, further apart. And he tries to reproduce that. We've seen what Wasserstein distance is, so we're going to, I just want to stop actually. So it's called coarse Ricci curvature. But here's the picture. Instead of a sphere, you have a probability measure. So you have a family of measures indexed by the point, X and Y. And now you sort of average over these distances and you get the Wasserstein distance on this side and 1 minus kappa. That kappa is the curvature, which I've called R over there because I wanted to keep it consistent. So this actually is very nice because it's not difficult to compute. You stick it in your program and it really goes quickly. And I just wrote down some examples. For the discrete cube, it turns out to be 1 over n. He actually found it for Glauber dynamics and was able to reproduce a lot of results. And those are our 3 problems we visited. It's very nice. So positive R implies normal concentration. But I'll tell you what, in the interest of full disclosure, you can get way better concentration on a discrete cube using different methods rather than curvature. But it's an easy way to do it. The best concentration of measure on a cube is with 1 over n, no, with an n, and with r you get 1 over n in the exponent, so it's way better, but this is just an easy way to get it. So this is just various problems that positive curvature gives you a great handle on a solution for this, in both in the discrete setting and in the continuous setting. and that's for further reading. So sorry it became compressed in the end, but the point, if you want to take home 1 point or 2 points from this, think about the various problems that we have of mass transport, the ones that discuss concentration. And if you ever read about these, it'll open windows into more problems, isoperimetric inequalities, which tell you, which really give you a handle on what's called conductance, how quickly, what is the relationship between sets and their boundaries, how big are the boundaries compared to the set itself, and so on. So these are all very important problems to work on, even when you're dealing with Markov chains, and they're very active areas. And if you can think about a geometry for Markov chains, something to give you ideas, what would can you define some sort of tensors, a geometry, and figure out a way that's a nice definition of Ricci curvature. Well, I think actually Olivier has a very nice definition, so maybe that's done. But if you can improve on it, and a nice definition is one that will give you results that's useful. And so I think it's a great place to work. It's a nice avenue for you if you want to go down there. And now my throat is dry and I am done.